One of the projects that we have that we're also really excited about is trying to understand what happens when you take two different materials and you put them together. The reason this is so interesting, right, is if you think about industrial catalysts that are out there, things like the things that do Fischer-Tropsch chemistry to take light hydrocarbons and make them into long-chain hydrocarbons, or the things that do catalytic reforming to take gasoline and change it in different ways and increase the octane rating. All of those industrial catalysts are almost never a single material. What I mean by a single material is a single chemical entity, the single crystal structure of the material. Instead, what they really almost always involve is a catalyst on a particular support or in conjugation, basically bound to another different type of material. Think about it as maybe a metal and a metal oxide, something that contains both oxygen and the metal, and then just a pure metal. And if you think about that, the type of reactivity you can expose at the metal-metal oxide boundary is very, very different than the type of reactivity you can expose on the metal alone. And one of the things that we really want to explore in a systematic way is how we can apply those strategies, take them away from the sort of high-temperature, high-end, costly way that it's done now industrially, and turn it into a low-temperature process that could be used to convert electricity into a fuel, for example. And one of the areas we're looking at this is in a really exciting project where we want to actually take CO2 out of the air and convert that directly into a liquid-based fuel. This is a really, really hard problem, as you might imagine. It involves a complex reaction where you're making and breaking a lot of bonds. Like we talked about before, when you make and break a lot of bonds, that's when it gets really hard, the selectivity gets really hard, and you have to pay a lot of energy penalty to make that reaction go quickly. But what we'd like to do, and we're making a lot of progress in this area, is be able to figure out how to take CO2 out of the atmosphere and convert it directly into a value-added product like ethanol that could be then combined into a fuel or a higher hydrocarbon or even a commodity chemical that we couldn't access otherwise, like formic acid. And the strategies that are involved in that, we think, have a lot to do with exploiting what happens at what we call these phase boundaries. What we mean by phase is just the boundaries between two dissimilar materials. It could be one metal and another metal, a metal and a metal oxide, a metal and a metal sulfide, for example. But it's at these boundaries where you have this really unique reactivity that's totally different than what one material or the other material could do by itself. And so we want to exploit that reactivity to be able to do selective chemistry in this really, what would be a game-changing type of way to make synthetic fuels. So one of the things that we envision is basically having flue gas streams where you'd concentrate the CO2 and be able to use that, couple it with a solar farm to be able to actually directly make liquid fuels using basically sunlight or a renewable energy source. The attraction of that is that if you're able to take CO2 and make a liquid fuel, now all of the challenges that used to be there with making hydrogen and doing storage and all that goes away. It becomes a lot easier because now you have an energy-dense, volumetrically dense way to actually store that energy. And that can be combusted directly into the current infrastructure, or you could use a fuel cell to be able to recover that energy later on. So those are all the opportunities that are afforded by now doing a much more complicated but yet a much more energy-dense sort of reaction.